which is preparation of the optimized lipid-coated calcium phosphate nanoparticles for enhanced siRNA delivery to breast cancer cells. Since the RNA interference was awarded the Nobel Prize for medicine in 2006, billions of dollars has been invested in the gene silencing improvements, and at least 22 RNA-based drugs have entered the clinical trials, and 5 among them are for cancer therapy, and more in the pipeline. Despite its powerful promises as a drug, siRNA requires a sophisticated delivery system because of its rapid degradation in the circulation and the insufficient accumulation in the tumor site, and the inability to cross the cell membrane to access the cytoplasm. As shown in this table, there are the table listing 5 RNA-based cancer therapy drugs in clinical trials. Lipid nanoparticles are used to systemically deliver the siRNA to the site of tumor. So we can conclude that delivery is one of the key to realize the potential of the RNA interference for cancer therapy. An ideal vector for the siRNA delivery should meet the following criteria. First of all, the delivery system should be biocompatible, biodegradable, and non-immunogenic. Secondly, the vector should provide protection of the double-stranded siRNA from the attack by the serine nucleases. Other characteristics include invasion from the mononuclear phagocytic system non-circulation, extravasation from the vascular endocellular barrier, diffusion through the extracellular matrix to be taken up by the cancer cells, and escape from the endosome to release the siRNA to the cytoplasm. The inorganic calcium phosphate nanoparticles have many excellent properties as a nanocarrier for cancer therapy. Firstly, calcium phosphate is of high biocompatibility and good biodegradability, as they constitute the major inorganic phase in human heart tissues. Calcium ions are also known to form complexes with a nucleic acid backbone, and thus may provide protection of the double-stranded siRNA from the serine nucleases. As we know, calcium phosphate is pH sensitive, so the nanoparticle can be dissolved in the acidic pH value of the endosome, increasing the osmotic pressure, resulting in the rupture of the endosome and thereby release its cargo into the cytoplasm. Recently, by coating the calcium phosphate nanoparticle with an oleic lipid, DOPA, and further coated with other membrane-containing lipids, the lipid-coated calcium phosphate nanoparticle was developed and possesses a colloidal stability in the aqueous solution, and can carry nucleic acid, peptide, hydrophobic drugs at the same time. After that, by simply inserting some hydrophilic polymers to the outer layer, such as polyethylene glycol, the LCP nanoparticles can be partially invisible from the immune recognition, and thus may increase the circulation time in vivo. Besides, the functional group at the distal end of the pad can be easily modified with multiple targeting ligands. All these features makes LCP nanoparticle a promising candidate as a nano platform of siRNA for cancer therapy. Recently, 3 siRNAs target CMYC, MDM2, and VEGF were co-formulated in LCP nanoparticles by Professor Li Wang's group. Such a formulation caused the simultaneously silencing of the 3 oncogenes in the metastatic nodules and resulted in significant inhibition of lung metastasis at a relatively low dose without any observed toxicity. And there are increasing studies report that LCP nanoparticle can efficiently deliver siRNA to the target tumor cells and stimulate significant RNA interference effect. In our study, the LCP nanoparticles were prepared using a modified two-step method. In the first step, briefly, during the synthesis of the particle, the amphiphilic and anaolic lipid dopa were added into the microemulsion to form the calcium phosphate cores with the first layer lipid coating. And after that, the second lipid layer can be easily coated outside the first layer by a film rehydration method. Although the preparation process of the LCP nanoparticle seems pretty simple, but the formation of the precipitation of the calcium phosphate has been described as a fairly complicated process dependent on several parameters such as calcium and phosphate iron concentration, ionic strength, pH value, the nature and the concentration of the surfactants. The calcium to phosphate molar ratio is also very important because the ratio may initiate different kinetics of the reaction and resulting in precipitations with different properties. So how will the calcium to phosphate ratio influence the properties of the LCP nanoparticles? Here I will to address the structure of the LCP nanoparticles again. It contains a calcium phosphate core which incorporates siRNA or other hydrophilic molecules, and the outside is the asymmetric lipid layer with or without pegylation. The reason why the lipid layer can be coated outside the core is because the amphiphilic and anaolic lipid dopa, which has a phosphate group, can stay at the interface of the microemulsion and interact with the calcium phosphate core through binding with the surface calcium iron. And as we know, the pure small lipsome size is from 50 to 100 nanometers. But in our case, the size of the LCP nanoparticles can be reduced to about 30 nanometers. So we can emphasize that the size of the LCP nanoparticle is predominantly dependent on the inner calcium phosphate core. Previously study indicates the calcium to phosphate ratio indicates the influence of the calcium to phosphate ratio on the pure nanostructured calcium phosphate nanoparticles. While it is unclear how the calcium to phosphate ratio will influence the properties of the LCP nanoparticles in the presence of the dopa, because dopa may substitute part of the phosphate group on the surface. So in our study, we aim to elucidate the effect of the calcium to phosphate molar ratio on the particle size and the stability of the synthesized LCP nanoparticles, and the siRNA loading efficiency and the protection of the loaded siRNAs, as well as the cellular uptake efficiency and the cell growth inhibition of the optimized LCP nanoparticle we synthesized. Firstly, the particle size and the data potential of the LCP nanoparticle prepared at a different calcium to phosphate ratio were tested by the dynamic light scattering. And shown in the picture, the particle size decreased with the increase of the calcium to phosphate ratio from 25 to 100, and the size remains unchanged from the ratio of 100 to 400. Meanwhile, the lithium potential decreased slightly with the increase of the calcium to phosphate ratio, which may be relevant to the related to the relevant amount of the anaolic lipid dopa. Then the LCP nanoparticle were used to encapsulate the siRNA mimicking site 3 label dsDNA using 3 different methods. As shown in the picture, obviously, method 3 led to the highest encapsulate efficiency, where half amount of dsDNA was separately mixed with the calcium and phosphate solution. After that, the encapsulate efficiency and loading capacity of LCP nanoparticles prepared using method 3 at different calcium to phosphate ratio were tested. As shown in the figure B, the encapsulate efficiency of LCP prepared at the molar ratio of 50 and 100 were significantly higher than that of the LCP prepared at a ratio of 200 and 400. In addition, the loading capacity increased with the increase of the molar ratio. This data suggests the calcium to phosphate ratio is critical in controlling the encapsulating efficiency of the LCP nanoparticle. And we found that the lower calcium to phosphate ratio resulted in higher encapsulating efficiency and more LCP nanoparticles, but the loading capacity per particles is relatively low. So as a trade-off, we may suggest calcium to phosphate ratio of 100 to be the optimal to load the siRNA with reasonable high encapsulating efficiency and the loading capacity. After that, the protection of the siRNA loaded in LCP nanoparticles from the serine nucleases at different calcium to phosphate ratio were tested by the electrophoresis. As clearly shown, after 1 hour incubation with serine, naked siRNA was degraded and there was no siRNA left after 2 hour incubation. We also observed that siRNA incorporated in the LCP nanoparticles prepared at the calcium to phosphate ratio of 400 was degraded quickly, and there was almost no siRNA left after 4 hour incubation. Relatively, there was a large proportion of siRNA was protected by LCP nanoparticles prepared at the ratio of 50 to 200 in 2 hour incubation with serine, and the protection can be extended to 4 hours. And we also found that the protection provided by the LCP nanoparticles prepared at calcium to phosphate ratio of 100 seems to be the highest. So considering the loading capacity and the protection of siRNA protected by the LCP nanoparticles, we may suggest the calcium to phosphate ratio of 100 as the optimal ratio to prepare LCP nanoparticles, which will be used in the subsequent testing. These are characteristics of the optimized LCP nanoparticles. Shown in the picture, the size of the calcium phosphate core is about 20 nanometers. And the size of the LCP nanoparticles increased to 40 nanometers after coating the second lipid layer. When loaded with the functional cell death siRNA, the size remained unchanged, and with the data potential of minus 15 millivoltage. And the TEM picture confirmed the hollow spherical structure of the calcium phosphate core and the outside lipid coating membrane after negative staining. In addition, the XRD pattern and the FTIR spectral confirmed the formous calcium phosphate phase in the LCP nanoparticle. So what's the chloride stability of the LCP nanoparticle we synthesized with negative charge? So the chloride stability of the LCP nanoparticles was tested in the 10% serine contained medium, and as well as in PBS at 4 centigrade. As shown in the picture, the LCP nanoparticle can maintain its size range within 24 hours in serine contained medium, as well as in PBS, even after 1 week in PBS at 4 centigrade. In addition, the cytotoxicity test further confirmed that the blank LCP nanoparticle of low cytotoxicity in vitro within a large concentration range. In order to examine the pH-sensitive RNA release property of the LCP nanoparticles, the dissolution of calcium ions from the as prepared LCP nanoparticle were tested in various pH value. As shown in the picture, LCP nanoparticle exhibit certain degree of the dissolution of the nanoparticles at a different pH value, and the accumulated dissolution of LCP slowly increased to 40% at the pH value of 6.5, while LCP nanoparticles stay pretty stable at the pH of 74. This results suggest that LCP nanoparticles have a favorable property of pH-controlled dissolution, which may induce pH-sensitive release and endosome escape. After that, in the in vitro cellular uptake of the LCP nanoparticles loading with the size-free labeled dsDNA were tested on the human breast cancer cell line MDA-MB468. Showing the picture, the cellular uptake of the nanoparticles represented by the mean flow cytometry increased gradually with the concentration in the culture medium, indicating the cellular uptake of the LCP nanoparticle is dose-dependent. The confocal microscopy image also show enhanced size-free dsDNA labeled LCP nano delivery efficiency provided by the LCP nanoparticles. At last, in order to preliminarily test the anti-tumor effect in vitro, the cell growth inhibition was tested on the human breast cancer cell line MDA-MB468 with mTDSA. As shown in the figure, the cell viability of the cells is siRNA dose dependent, and as a comparison, the commercial delivery agents, oligofactamine, can kill about 40% of the cancer cells at the siRNA dose of 8 nanomolars. At the same siRNA dose, our LCP nanoparticle can kill about 83% of the cancer cell with a much higher inhibition effect than the commercial transfection agents. The morphology change and much less cancer cells in the LCP-CD siRNA treated group also confirm the cell growth inhibitory effect. This is a summary of our current work. We have successfully synthesized the LCP nanoparticle with a size of about 40 nanometers, which places an asymmetric lipid bilayer and with selective charge. The particle size and the zeta potential were predominantly determined by the calcium phosphate ratio. More interestingly, the loading efficiency of the siRNA and the protection of the loaded siRNA provided by the LCP nanoparticles were also significantly determined by the calcium to phosphate ratio. And our in vitro tests also suggest that the LCP nanoparticles we synthesized can efficiently deliver siRNA to the MDA-MB468 cancer cells and more efficiently inhibit the cell growth comparing to the commercial transfection agent. At last, I need to give my sincere thanks to my advisory team in Australia Institute for Bioengineering and Nanotechnology in the University of Queensland. And I also need to thank the Chinese Scholarship Council for sponsoring my study in the University of Queensland. Thank you for your attention.
Thank you, Ms. Tang. Any question from the audience? Yes, please.
So what do you think the potential applications of your system?
Since there are increasing study reported that the LCP nanoparticle can efficiently degrade the siRNA to the tumor cells, LCP nanoparticle is an attractive option for siRNA systemic delivery. And many reports have reported that the LCP nanoparticle can be used in vivo therapeutic applications. Maybe in the future it can enter the clinical trial as well.
Okay, any more questions? So, Ms. Tang, you have shown that the LCP nanoparticle can have an anti-tumor efficacy in vitro, right, for the breast cancer. Have you ever tried the in vivo model using xenograft?
Unfortunately, we haven't tried it yet with our LCP nanoparticle with negative charge. There are many reports that LCP nanoparticle with positive charge can successfully deliver the siRNA to the cancer to the cancer. Yeah.
And also, one of the data show that the ratio of the calcium to phosphate 400, right?
Yeah.
It is doesn't protect the snRNA from RNA digestion. Can you speculate why?
To my knowledge, I think it's because the mechanism of the calcium potassium 2-phosphate formed with the nucleic acid.
Mm.
Of course, at the higher ratio of 400, maybe there are not enough phosphate ions to form the complexes with potassium.
Mm.
So more siRNA were anchored on the surface of the complexes, so may make it vulnerable to the nucleases.
Okay, thank you.